Okay, in the little introduction, we looked at some examples of, some known very important equations. We talked about the difference between linear and nonlinear. We kind of organized the nonlinear into, a hierarchy according to how bad they really are. And we talked about some themes. We identified some issues that arise, and we talked about some, themes that, you will see again and again. I want to talk right now about a really important class of examples. One of those examples that we studied already, the minimal surface equation, that falls into this category. It is a variational problem. A lot of physical and geometric problems fall into this category. If you have some physical or geometric situation, configuration, or system, whatever, it will seek the configuration in which the energy, I'm using it loosely, what it is depends on, the context or, what physical or geometric situation you're studying. But the system will seek the configuration that minimizes the energy. Here's a simple example. Let's see if we can find the curve that minimizes the length between 2 points in the plane. Okay, a curve that minimizes length will probably not do something like that, right? Because there'd be no reason to add on a whole loop. And so, a minimizer, you can probably expect it, like right here, this is the implicit function theorem that we talked about the other day. You've got a curve that locally, and you don't look at, when I say locally, you don't look at an arc down here, you look at an open set up here in the plane. No matter how small you choose this open set, it will not project to the graph of a function over either axis. But a minimizer you will expect a minimizer to project to be the graph of a function over either the horizontal or the vertical axis. Okay? Also, there would never be a reason for it to do this, right? Because the shortest distance between 2 points, you're not going to go around a corner. And so a minimizer will probably also be at least of class C1. It will probably have at least one continuous derivative. So your minimizer you expect the minimizer to be a differentiable function a function, not just a random curve, but the graph of a function. The graph of a function, you expect your minimizer to be the graph of a function to project to be the graph of a function over either the horizontal or the vertical axis, and for that function to be differentiable. And so let's write the length. That curve will be the graph, can be expected to be the graph of a function, like f. Okay? The length of f would project to be the graph of a function over some interval in either the horizontal or the vertical axis, and be differentiable. So your length is your length formula, right? Okay, let me say this, I think in my calculation, these are not partial derivatives. If you don't mind, I'm going to write this like this, just so I don't have everything up here, and also so I can put a t in. But it's not a partial derivative. I'm just going to write it that way if you don't mind. But it is not a partial derivative. It's still just df dx. Okay, here's my length formula. Now, suppose that f is a fixed but unknown minimizer. And suppose that G is any other function that vanishes at A and B. We're going to want to take its derivative also. So let's say that G is any other C1 function that vanishes at both A and B. Then this function, and again, T is not the, you remember how to like multiply, add, I'm adding functions and I'm multiplying a function. So here's a new function, and because G vanishes at the endpoints, this function also, its graph also goes between these 2 points, all right? But if f is a minimizer, then the length of this new function for any choice of G satisfying this and for any real number T, this length will be bigger than that of our minimizer. Right? A minimizer, if you're going to view, let me say it this way. F is our minimizer, fixed but unknown. Now we're going to take any G, for any G that is that is C1 and vanishes at both A and B, we multiply by a constant T and we form a new function. The graph of this function also goes between the same 2 points, right? Because that's where you use the fact that G is 0 at both A and B. Because F is the minimizer, fixed but unknown, the length of F will be less than or equal to the length of this new curve. But now view this. Sorry, view this as a function of one variable, T. So if this is so when T equals 0, you get this. You have F, right? That means that the derivative with respect to T of this length should be equal to 0, right? Because we just from Calc 1, because we are at a minimum. Okay. So let's calculate it. Use your formula for length and substitute in the new function f plus tg, right? This is the length of the graph of the function f plus t times g, right? I just put it into my arc length formula. Okay, that's the length. Now take the derivative. Now take the derivative with respect to t, right? Differentiate under the integral sign. So you have this whole quantity. This was raised to the 1/2, so the derivative is 1/2 this, all raised to the power minus 1/2. Now it's a chain rule problem, times the derivative of what's inside with respect to t. So I have 2 times now this quantity, fx plus tgx, right? Chain rule again, times the derivative of what's inside with respect to t. So I get this. Okay? Now, do the recipe. Evaluate at 0, right? These calculations, you will practice some of them. They're a lot of fun. But you'll see that it gets worse before it gets better. But you just hang in there, because now you're going to set t equal to 0. So a lot of this stuff is gone. Okay, and then this is all that's left. This is all that's left. Now, next step, I'm going to use integration by parts to express this as something times g. Okay? What we had a moment ago, we had gotten this far, that the derivative of this quantity of the length of this new curve f plus tg with respect to t is equal to this integral. Now you're going to use integration by parts. When you move the derivative off of g and onto everything else. This is what you get. So far I've used in two places the fact that g is 0 at both a and b. First of all, without that, this new function would not be a graph between the same 2 points. Now you're using a second time in your calculations. It's the fact that it's because g is 0 at the endpoints that I don't pick up any boundary terms. Remember, you've got, in your integration by parts, you have uv at the boundary minus v du. Okay, there are no boundary terms because g is 0 at the boundary, at both boundary points. Okay, so then you've got this. Now, here's the crucial part. If f is a minimizer, then this should be 0. This derivative should be 0 for all choices of g. This derivative should be 0 for all allowable choices of g. The only way that can happen is if it is this first term that is 0. The only way this integral can be 0 for all choices of g is if this first term is 0. And now you just do some calculations. This will be 0 if and only if the second derivative of f is 0. Let me go back to the usual notation. Okay? The only way this integral can be 0 for all choices of g is if it's this first factor that is 0. Then you just do some calculations and you see that this is 0 if the derivative of the numerator is 0. Okay? This is called, in this variational approach, the familiar equation of a straight line is called the Euler-Lagrange equation. This is called the Euler-Lagrange equation. Okay, let's look at another physical geometric example. Very, very similar. I mean, this one was, so familiar that, of course, you ended up with the equation that you already knew. If I asked you what differential equation is satisfied by a curve that generates a surface of revolution of minimal area, well, that equation, is not so, is not so familiar. So let's look at the surface area problem. So this is another geometric example. One variable that you can work out back in calculus. Here's the problem that I'm interested in. I'm going to take a curve, the graph of a function. My curve is the graph of a function. So f positive on some interval. F is positive on some interval, and it's differentiable. One continuous derivative. Okay, and then I'm going to form I'm going to rotate the curve around the horizontal axis to form a surface of revolution, and I'm going to calculate the surface area for a given f. To calculate the surface area, to produce a formula that gives you the surface area for the surface of revolution generated by such an f. That's a problem you can do back in Calc 2, right? But right here, what we're saying is, if these two endpoints are fixed, what is the curve? For what choice of f is this minimized? Well, you'll do some calculations maybe related to this problem later. But that's not what I want to do right now. I want to draw your attention to this. To make my drawing simple, let's say that the endpoints were at the same height. One thing I want you to notice is that there would never be any reason to bulge above the horizontal, because the surface area, when you rotate this curve around the horizontal axis, the surface area that's generated by this arc is greater than the surface area that's generated by replacing this segment by the line segment. Okay, but now notice, the concatenation, if I replace it so that this, if the curve bulges above the horizontal, then it's certainly not going to be a minimizer, because the surface area generated by replacing it by this line segment is smaller. So now, but this concatenation, replacing it by this line segment, the concatenation of these two curves is no longer C1, right? And just like once you work out this formula, you'll see, just like in the length formula, you need a differentiable function. Okay. So you would like, and by the way, we said we do expect the minimizer to be C1, but you don't want, because of course you can then, first you make your surface area smaller by replacing this bulge by this line segment. Well, that's still not a minimizer, right? Because you can cut off this corner. You can cut off this corner, but the problem with that argument is now you've introduced a layer of, introduced ambiguity, because how exactly are you supposed to smooth out that corner? Okay, well that's not what you want to do. Instead, what you want to do instead is expand your definition of differentiability to allow such functions, the concatenation of those two curves, producing a little corner here. Okay, what's the key? The key is, go back to the last problem. Integration by parts. Integration by parts is how you expand your idea of differentiability. Suppose you've got a function that is C1 in a domain domain omega. Could be one-dimensional, like in my example. Could be higher dimensional in the examples we're going to, occupy ourselves with during this course. You remember this notation? To be in class C1 means to possess continuous derivatives. U and its derivatives of order 1 are not just exist, but continuous on this open set. And by the way, speaking of notation, I know, right here, I know I kind of snuck something past you You can look this up even in a Calc 1 book, or we'll talk about it later. Because, you know, you see the problem, right? Derivative requires a limit. You have to be able to approach from all directions, which requires an open set. Okay, that's a detail. Okay, but here's some notation I don't know whether you know. This is the class of functions that are C1 and supported in a compact set in the interior. That doesn't mean it's not enough. It's not enough to V. To be in this set, it's not enough that V vanish at the endpoints. V has to vanish in a neighborhood of the endpoints. Okay. But suppose you have such functions. Then notice this. Do your integration by parts. So you're looking at the jth partial derivative. We used this in the last example. In integrating by parts, it's the fact that V is 0 at the boundary that means that you don't pick up any boundary terms. So your integration by parts, you just move this derivative off of U and onto V. Okay? So now you've got okay? That's integration by parts, where U and V are both nice C1 functions. But now, look, now you can turn this logic around. So if G, so you've got another function G, and it satisfies this. It has this property that whenever you multiply replace this by G. If you can find a function G that has this property that G times V equals minus the derivative of the integral of U times dv dx, and if that holds for all V, for all such V, then you call G the weak derivative. The weak derivative. If U is actually C1, then G is the derivative. But you remember, again, back from calculus, the class of integrable functions is huge. It is way bigger than continuous functions, continuous or even C1 functions. So G could be much more general. G could be much more general, but if G has a property that every time you integrate it against what you call a test function, a smooth or at least C1 test function, you get this, then it's like you're pretending that U is differentiable. You call it a weak derivative. This concept of weak derivative allows you now to calculate arc length or surface area for function with, and it allows you to include. It allows you to include functions like this concatenation. They're not literally C1. Okay. Since we mentioned it the other day, let me just. We were talking about function. I just mentioned briefly, some of the function spaces that typically arise in the study of PDE. We've talked today about CK a lot, but I mentioned back on the first day HK. This is the set if CK Your CK is the set of solutions, set of functions whose U and its derivatives of all derivatives of up to order K are continuous. That's what those elements make up CK. HK, to qualify to be in the function space HK, U and all of its derivatives of up to order, all of its weak derivatives of up to order K lie in L2. That's the space HK, it is called a Sobolev space. You might wonder, okay, I do expect my when I've finished solving that problem, I do expect my minimizer to be C1. It's just at intermediate steps. It's just at intermediate steps that I might want to include, amplify expand my function space to include things like this. They're not literally C1. But you might ask, I think this problem kind of motivates why to do this, but still, you might ask yourself, is it really necessary? I want to solve a differential equation, right? I want to solve a second order differential equation. Why can't I not just look, in C2, functions that, like if I want to apply the Laplace operator, shouldn't you have two derivatives? Okay, why do I want to consider these function spaces? And by the way, just like in Calc 1, what we just mentioned, the class of integrable functions is huge, much bigger than continuous functions. Okay, why? There are a couple of reasons. First of all, the origin of the problem, just as in our example, may be such that even if you expect your solution or your minimizer to have greater regularity, to have higher regularity, your problem might arise in such a way that at intermediate stages you want to consider functions, like this. Here's a second reason. As we said a minute ago, these spaces are very big. They're bigger. If you want to prove existence, it might be easier to look first in a bigger space, where something's more likely to exist. It might be easier to prove existence first in a larger space and then prove regularity after the fact. By the way, that's a second order differential equation, but solutions to this actually have derivatives of all orders. So it might be easier for you, it might be better, to look for solutions in the larger function space and then try to prove regularity of solutions after the fact. Here's another simple example. Deep, not simple, but simple, like feels simple because it is familiar. Think of your undergraduate course in complex variables, right? You got your Cauchy-Riemann equations. That's a first order. Those are first order equations, right? But think about the implications of that. If a function solves those two little first order equations, then it's analytic. That means it possesses derivatives of all order. And not only that, but it has a convergent series expansion. Doesn't get any stronger than that, right? Okay, here's a third reason. Here's a third reason to consider these integration-based spaces, these big Sobolev spaces, L2 spaces, and big integration-based spaces. L2 is a Hilbert space. So now you've got all of your machinery. It's got an inner product. Inner product equals projection, and so now you've got all of your machinery related to length and projections. Maybe Maybe you've even got an orthonormal basis. Maybe you even got an orthonormal basis, for your operator. Okay, very good.